So today's lecture then we will be focusing on carrier drift, the scattering mechanism with the drift current, the conductivity and the mobility of these charges. So what do we mean by mobile charge carriers in semiconductor? Okay, there are, we say, three primary types of carrier action occur inside semiconductor. One of them is the drift, diffusion is the second one, and the recombination generation is the other one. Okay, but today we will be only talking about the drift. In the coming lectures, we will be discussing diffusion and recombination generation rate. Okay, the drift is caused, or the motion of any particles will happen under the influence, we say, of electric field. So what if I don't have electric field? If the electric field is zero, then the drift current will be zero. Diffusion will be the particle motion due to the concentration gradient or temperature gradient. So we will be working with diffusion under the rate like dN by dx or dN by dt, where N stands for the concentration, so you will find the rate. And then the recombination generation rate as well. So if you recall from last year when we studied the current for the diode, for a PN diode, or for the bipolar junction transistor, we talked about I being the current referred to as the reverse saturation current times exponential term of EB على KBT. While here what we will be doing is understanding the I0, we call it, that's reverse saturation current, came from what? We took it in as an application as constant, while here it is the sum of all these currents, the drift plus diffusion plus recombination for each particle. So let's start with the drift current today. Before we start, we want to know how electrons are moving. So if we are talking about the free electrons, so that means in space, we say that the external force is equal to the minus the charge times the electric field, which is the free mass times acceleration, or it is the momentum per unit time. So that's in free space. We refer to it as momentum per unit time since we want to relate the electrons inside the semiconductor. So it's easier for us just to implement momentum and put the change with respect to the mass of the electron. So the conductivity effective mass is the one that takes the replacement of the all the effect of the internal force, since the internal force in semiconductor is very complicated. So here when we talk about F, so it's the external plus the internal force, which is still equal to the charge times the electric field, and we take into consideration the effective mass rather than the free mass times the average velocity over the tau scattering, which is the relaxation time, we call it, or the microscopic parameters, while we will talk in a minute about the macroscopic parameters as well, and how we relate both to each other.
دكتور بس شو هي الديكي؟
Decay is the vector quantity. That's why when I write Boltzmann constant, I put K subscript B. That's the vector in the wave function. If you go through Schrödinger equation with the time dependent and time independent equation, you will find the solution for the electrons. We took just the solution to it and we reached for the momentum. Usually you write it h bar k, right? So what's it changing as a momentum? Momentum is h bar k. So now it's h bar dk by dt. So it's a time dependent. Okay. So that's the momentum per unit time. Okay, carrier drift. Okay, when we are talking about an electric field, that means which is an external applied voltage. Okay, before when we used devices and when we put PN diode and being the P connected to the N without an external potential, if it was a battery or a source or an AC or DC, we said that it has zero potential drop, which was just due to the motion of electrons inside the semiconductor without the applied field. While when an electric field is applied, you're talking about the mobile charges carriers, which is being accelerated by this force. But of course, inside the semiconductor, the electrons, they get scattered, like they lose their position. They don't move in, like in a straight line, while you say that the electron drift is in the direction opposite to the electric field, but you take it as a net current rather than saying due to the scattering condition. So that's why I say electrons, they scattered, but we treat them as moving with an average drift velocity. So we will take the average velocity. We will say, before and after collision. Now we will take this approximation that we are talking about in order to derive the current, the relationship between current and mobility of the electron or the conductivity of the material with respect to the relaxation time, the time that it takes to collide between electrons. Okay, so what we do is we say we take this approach only applicable under low electric field. So we are in a, like the electronic devices, we treat them in low to moderate electric field where the mobility of the electron are constant as a function of field. Okay, so what are these assumptions that we have to take in order to derive the relationship between the mobility of electrons or the conductivity of the material and the current? First, we say that the electrons in the semiconductor do not interact with each other. So they are not, and this approximation, we say it's independent of the electron approximation. So in that way, we say electrons suffer collision from various scattering sources, and the time tau scattering describes the mean time between successive collision. We also want to say that the electrons are moving as inside the semiconductor as if they were moving outside, like in a free space in vacuum. So we said that the electric field inside the semiconductor has electron moving according to this equation, the h bar dk by dt, where k is the vector. Okay, so what's really going on? So let's really describe in between collision. What do we have? After the collision, the electron will lose all their excess energy. on the average, so that the electron gas is essentially at thermal equilibrium. This assumption is really valid only at low electric field. So that's why we are talking about the assumption that we made according to Drude approach. According to this assumption, we say immediately after a collision, the electron velocity is the same as that by the thermal equilibrium condition. So the average velocity is thus 0 after collision. So it doesn't have velocity after they have collision. And then we say that the electron gain a velocity between collision only for the scattered time, only for that time that it's required to have or it took for to do collision. So we say that the average velocity, this average velocity equal to minus E times the electric field times tau scattered over the effective mass, okay, equal to Vd. So in that case, we're no longer taking derivative. So you see what we are saying, we're back into the, if you write down the force as if it was outside the semiconductor, we said it's equal to minus E times the electric field, minus the charge times the electric field, equal to the external force. The external force is equal to what? Equal to the mass times the acceleration. Acceleration is V average over the time. So instead of taking the derivative dk by dt, so we already took the scattered time as being and the average velocity. And instead of the free mass, we put the effective mass. And all that, we said then, we can refer to this average mass as being the drift velocity. We refer to that average velocity as the drift velocity. So we can write down then the current. The current is defined as what? As concentration times the charge times the velocity. Okay, the drift velocity. So this is the drift current, and here we refer to the electrons, so we write minus n, the concentration of electron, times the, and you know the concentration of electrons is per cubic centimeter, we multiply it by the charge times the average velocity. So then we can say that the current, the drift current equal to the concentration Ne square tau scattered times the electric field times the effective mass. So we substitute for this drift velocity from that equation.
دكتور يعني هلا بعد الكوليجن الالكترونز ببطلوا يتحركوا؟
نعم. لا.
after collision.
نحن إذا عم نشتغل على low electric field عم نقول ال velocity depending on the applied field. الموبيليتي under low electric field to moderate هي fixed. الموشن اللي إلها is given for every material. هيدي هي الساين تاعت الموبيليتي الميو. ميو times the electric field بيعطيني the drift velocity.
بس بالسلايد الأول مكتوب إنه after collision الإلكترونز بتصير الفيلوسيتي إلهم زيرو.
الافريج after يعني خلص بس صار عندي هالدريفت فيلوسيتي، صار الكرنت عم بيعتمد على هود البارامترز. شفتي حولنا يعني حطينا الدريفت فيلوسيتي in terms of the electric field, the relaxation time and the effective mass. هلا إذا أنا أخذت هيدي الإيكويشن وعم بقول هيدي صارت my drift velocity، شو اللي عم بيتغير؟ يعني my drift velocity is proportional to my electric field. الإلكتريك فيلد اللي عم بيتغير and of course the scattered time. scattered time يمكن أن يكون عم بقول لك إنه والله the scattered time for this collision is equal 10 to the minus 9 second. So you see how fast it is. Okay, and then I say for an applied field of 5 kilovolt per centimeter, obtain مثلا the velocity. تطلع الفيلوسيتي، مثلا طالبه منكم طلعوا الكرنت، فطبعا نحن اخذنا الكرنت عم بيعتمد على الفاريشن of the electric field and the relaxation time. يعني I related my mobility of electron اللي هن بنسميهم الموبيليتي من إلا macroscopic property of the particle, and the conductivity of the material هي macroscopic property of the material, while the relaxation time is the microscopic properties of the system. So in that case, we can relate those mobility and conductivity to the relaxation time. ساعتها بقدر اطلع الكرنت. يعني الكرنت عم بيعتمد على كل هود البارامتر. نحن اذا رجعتي لأومز لو، أومز لو شو بيقول لك؟ هي ديفاين بيقول لك الكرنت the density، ما هيدا density current. نحن بعدنا ما دخلنا الاي اللي هي شو بتساوي؟ بتساوي ل A the cross sectional area times the current density. يعني هون عندي اليونتس تاعت هذا الكرنت density هي امبير بير سنتيمتر سكوير. اوكي، فاذا هو عرف لنا اومز لو ان by Ohm's law, the current density equal to the conductivity of the material times the electric field. يعني الكرنت عم بيتغير with respect to the electric field, to the applied potential على هالسيستم. ونحن شفنا هالشي لما كنا عم نعمل application، انه مجرد ما غير انا السورس عم بيتغير الكرنت بقلب الديفايس، وعم بياخد مش بس البلت ان potential، عم بيصير في عندي forward potential or reverse potential depending on the direction of current. فإذا طيب إذا عندي ال conductivity of the material عم بيقول لي من هيدي الإيكويشن I can go back to the drift current that I obtained by collision related to the scatter time، فصار في عندي relation of conductivity with the relaxation time. Okay. وباي definition الموبيليتي of electron هي بتساوي للدريفت velocity over the electric field. فإذا صار في أطلع أنا من هيدي الإيكويشن related to the equation before، فبيطلع عندي الموبيليتي of the electron equal to E times the scatter time over the effective mass. وبهيدي بنقدر نعمل الجنراليزيشن نحن وريليت من هالتو equation the conductivity and mobility of the material إذا كنا عم نحكي عن electrons أو عم نحكي عن holes، لأنه الإلكترونز بقلب الكوندكشن باند، الهولز بقلب الفالنس باند. هلا أنا حأرجع أعملكم الديريفيشن للكرنت وتشوفوا كيف اشتغلنا لحتى تقدروا تعرفوا. اوكي، نحن هون قلنا الافريج velocity of the electron is equal to minus E times the electric field على the effective mass of electron times the scatter time. For holes it will be positive, it's the charge times the electric field over the effective mass of holes times the scatter time of holes كمان، لأنه يمكن scattering time they are not the same. Of course, the effective masses for every material is related to the free masses, which is equal to 9.1 times 10 to the minus 31 kilogram. Okay, carrier scattering. هون نحن شو عم نحكي؟ عم نحكي انه عندنا لاتس سكاترينج وعندنا فونون سكاترينج. Okay, so by definition, we're talking about the impurity, the ionized impurity atoms, and the carrier scattering as well due to the force, the external force. And then we said that the net current in any direction is zero if no electric field is applied. So we said if there is no electric field, then since we're taking the average, it will be zero. Now, okay, again, the momentum, we're talking about electron momentum. So we're saying with every collision, the electron loses momentum that is assigned to it as the effective times the drift velocity, where the collision between collision, we gain momentum, which is minus the charge times the electric field times the scattered time. And the conservation of momentum then is this mass times the drift velocity equal to the charge times the electric field times the scattered time. We're taking the absolute value so we don't worry about the sign, because we know that the charge of the electrons is always negative. So we're taking that. This is how we obtain the relationship of the mobility of electron with the microscopic properties, the scattered time. And similarly, we take it for holes, so it's the same thing. Again, we said we rewrite the equation for the drift velocity and relate the electric field and the mobility to obtain these equations. And as you notice here that the mobility of electrons and for holes will be given for every material at 300 degrees Kelvin. So you see, if we have a sign, usually when we are trying to derive the current, we derive the current under 300 degrees Kelvin, so we can do the application and have a fixed or a constant mobility for every material will be listed in the table for you. So conductivity and resistivity. So here we written the drift current for holes and the drift current for electrons. So you notice that we have minus minus, so in both will be plus then. And we say that the drift current, the total drift current is the sum of the current for holes plus the sum current of electrons. So we can rewrite the equation in this form, saying that it's E P mu P plus E N mu N times the electric field, which is the conductivity of the material times the electric field. So really what we are saying for a fixed material, like if I'm talking about silicon, for example, then the conductivity of silicon will be known. Depending on the applied electric field, the drift current will be calculated. And we reach to the conductivity again, which has a unit of mho per centimeter, meaning Siemens per centimeters, which is the conductivity is the resistivity of the material is 1 over the conductivity. Okay, the whole drift current density then is equal to EPVD, and if we're talking about that's per unit area, if I want to talk about the current I, then I multiply by this cross-sectional area to obtain the current in amps. if I want to relate it to the material properties, meaning the width, the length, and the thickness of the material, then we know that the resistivity will be equal to, according to Ohm's law, R equal to V over I, which is equal to this resistivity of the material times L over WT, where L is the length of the bar over the width over the thickness, and rho is the resistivity. So sometimes you might have a problem given to you these parameters and you're asked to obtain the current, so you can convert it from this equation into that equation. By the way, you know, like any, although I recommend you read in your textbook, whichever make you feel comfortable. I sent you 2 PDF files, one by Sin and the other one by Sin and the other one by CZ. So both textbooks are good. You can, whichever you find easy to deal with, you read in it. But what I tell you as well, you will be only responsible for, you know, like the material that I, you know, present to you in the lecture. So any additional material you can just skip or read over, but no need to go in detail with it. Since this course is really intended for you as an elective course, and it should be simple enough for you just to understand the behavior of electrons and holes inside a semiconductor and how they are related to the application as a devices. So here I'm giving you the resistivity dependence on doping. So as you see, the resistivity of the, let's say, if I take silicon material, and I'm talking about the N-type, which is in the conduction band. So the density, as you see, the resistivity is varying according to the density. So as we increasing the density of acceptor or donor into the system, of course, for N, it will be the donor. For P, it will be the acceptor. So we notice that the resistivity of the material becomes smaller and smaller as the density of the donor or acceptor have increased. Since the resistivity is 1 over En mu n, so where N, the concentration of electrons, will be referred to it as the density of the donor. And here is for P-type material, the resistivity of the material is 1 over EP mu P. So hence we can rewrite, or as you see for silicon, we do not apply, you know, the compensated material doped with both acceptors and donor. Okay, now I want to show you as well how the mobility of electrons is dependent on the summation of Nd and Na. So the total dopant concentration, if we have doped, let's say for silicon, a P on one side and an N on the other side, so we have a Pn device, how the mobility of electrons is related at 300 degrees Kelvin to the density or to the concentration in the material. Now, here what I'm presenting is the mobility dependence on temperature. Since we know it is to the 3/2 from the equation that we obtained for the density of a state, We said the density of a state equal to √2/2, m effective to the 3/2, kBt, e to the half over pi square h bar cubed. Okay, so the temperature it's to the 3/2. So that means the mobility of electrons, since it depends on the density, it will be dependent as 1 over the, so we're taking it as 1 over, since we said that the mu equal to 1 over n. So it's inversely proportional to the concentration, so it will be inversely proportional. There is another equation that is important to know. We're saying that the kinetic energy, we refer to the thermal velocity, okay, to the Boltzmann and temperature. So V thermal depends on the temperature, and we say that the kinetic energy is defined as 3/2 kBt, which is equal to half mv squared, where m is the effective mass of the electron and v is the thermal velocity. So here we are talking about thermal velocity. That's why the kinetic electron kinetic energy as thermal velocity is referred to as 3/2 kBt. So here we do some example in what if we are talking about the 300 degrees Kelvin. We know at 300 degrees Kelvin, kBt is equal to 0.026 electron volt. The temperature and the effective mass. So the effective mass we multiply by 0.26, and the thermal velocity is given times the charge. So I'm talking about the equation of the velocity from this equation. If we are talking about the free path, the mean free path, so we need to know that now it's another, before we go, let's go back before we go to this equation. Okay. In here, what we did, we just substitute for kBt. Okay, we multiply by 3 over the half is gone, so 3 kBt equal to the m effective times the velocity square. So V thermal is the square root of a 3 kBt over the effective mass. So 3 kBt is equal to 0.026 electron volt, and I have to change it from electron volt into volt. That's why I multiply by 1.6 times 10 to the minus 19 joules per electron volt, and then just to have the units in meter per second or in centimeter per second. So you know this conversion came from where? Okay, and the 0.026 is from the kBt at 300 degrees Kelvin, knowing Boltzmann constant, so it will be tabulated for you to know, and the effective mass is given for silicon material. Now we want to, as well, sometimes you're asked to obtain the mean free path between collision. So if you want to find the distance traveled of electrons, it is equal to this thermal velocity times the scattered time. I'm just adding to you or giving you this equation so you will know when we do an application, maybe what we can do is we can do on Tuesday, next Tuesday, we can do a problem session. If I have time, what I will do is I will send you some exercises for you to practice, then we will go over them on Tuesday, since Monday is a holiday, so you can sit and work at home. Okay, now we are saying that the probability, this rules, what does it state? It's saying that the probability that a carrier will be scattered by some mechanism, let's say we call this mechanism I, in a time period dt, then we say that this probability is dt over tau I, where tau I is the time it takes between scattered event to happen in this mechanism. So you're taking the sum of all scattered particles. So what we are saying is saying that they are, you know, going the phonon and the impurity as if they are going in parallel. So we're saying that the total scattered time is calculated, although, you know, like in any exercise that we will do, I will be giving you the scattered time. So no need for, unless I tell you to calculate the impurity scatter time or the impurity immobility, which I doubt I do. It's not for you, it's just for you to know that we have a scatter time that, yes.
شو هي الفونون؟
It's, if you know, it's the electric field when it's being, when the electrons, you know, like we call the electrons as being fermions, right? But if I'm talking about here, I'm saying that the particles, the scattered particles, okay? So the particles are phonons, okay? Did I answer your question? I guess so.
Yes.
Okay. You see, phonon scattering, it's the lattice scattering, so it's the material. While the impurity, it's the dopant ions. Okay? You already have phonons scattering, which is the electrons inside the let's say, for example, I'm talking about silicon. So due to temperature, electrons might go from valence band to conduction band. So that we say by emitting or absorbing, we call it phonon. Okay, phonon scattering, then it's the built-in motion of particles, you know, like electrons and holes, due to the lattice scattering, due to the temperature changing, maybe due to vibrating, you know, like maybe your mechanism is not fixed and you have a vibration that will cause electrons that are within the lattice itself have shifted from valence band to the conduction band. So we say that the electrons in the conduction band got absorbed and then they emit back into the valence band. So this we call it phonon scattering. While if I have doping material added to the pure material, to the lattice, then in this case I will call it impurity ion scattering, and here I will have the impurity scattering time that I have to account to it. Okay, so phonon scattering, limited mobility, decrease with increasing temperature. As you notice when we presented the temperature on the chart before, I showed you that the mobility will decrease as of increasing temperature. So then in this case, we say that the phonon scattering, the phonon mobility are proportional to the phonon scattering time, which is proportional to 1 over the phonon density times the thermal velocity. Okay, so that's why which we will say it's a proportional. You notice that proportional to the minus 3 over 2, the temperature. If I go back, if you want to go back to the slide so you can See what I'm talking about? So we have to go few more slides. One more slide, I believe. One more. Okay, here. So you notice temperature, the lattice scattering. We said that the mobility, this mobility is proportional to T to the -3/2 inside the inside the lattice scattering. But if it was due to the impurity scattering, it will be proportional to the 3/2. So now we are into which one? We were here? Okay. So the mechanism, we talked about it and we showed the relationship, and we said that then according to the phonon mobility, they are proportional to the T to the -3/2. So we are talking about the lattice mobility. Okay, and this is proportional to the square root of temperature, the velocity, and here what we mean by impurity ion scattering. Now, impurity ion scattering, if I'm talking about boron, that means I'm talking about what? About losing electrons, because we give an electron to the boron atom, then we will have an ion which is negative, while for electrons, for arsenide ion, that means we are getting a positive ion. So there is a less change in the electron's direction in the electron travels by ion at higher speed. So we're saying that there won't be any change. Ion scattering, limited mobility, increases with increasing temperature. And we got this relation. We said the impurity, in impurity, now photons, so due to the doped material, if it was an acceptor or donor, then we are saying that the impurity mobility is related to the temperature to the 3/2 over the sum of the density of acceptor plus density of donor. Okay, and here I just want to note to you that we will be working in this region of materials. We will not be having electric field, high electric field, where the mobility of electrons start changing. So we're taking here, which is the slope will be then constant, okay, along the same. So we are working with electric field less than 10 to the power 3 volt per centimeter. Let's do some resistivity example then. We know that the resistivity, okay, we're given that it's a silicon sample doped with 10 to the 16 per cubic centimeter boron. Then I want to calculate the resistivity of the material, which is equal to 1 over E n mu n plus E p mu p. And as you know, this is the element that will create a p-type material, so the resistivity will be due only to p, so it's 1 over E p mu p. And then we're given the charge, we know the charge, we given p is the 10 to the 16 per cubic centimeter, and the mobility of silicon at 300 degrees Kelvin is equal to 450. So the result will be 1.4 ohms centimeter. So you see that the important of this course is to learn how to understand physically, you know, the derivation from, you know, like in today's lecture is how do we obtain the current, the drift current related to the electric field, mobility of electrons, and the and the time, the scattered time. So from that we can obtain, if you want, if we go back to the previous lectures, I mean to the previous slide where we did the derivation of the current. Still one more. Okay. Here, when we went through Drude approach, we went to obtain the relationship between the current and the mobility, and the relaxation time, electric field, and the effective masses, the concentration. So this is what we really have to know how to derive and to obtain. So in that case, we have reached now to the summary of the lecture today. So what we have is, then we said that the electrons and holes can be considered as quasi-classical particle with effective mass m effective. The reason for that, so we can treat the electrons inside the material as if it is a free electrons, just by you know, taking the relationship between the free mass and the effective mass of the material. We said that in the presence of electric field, then the drift velocity will be mu times the electric field, where mu is the carrier mobility. Then we relate the conductivity of the material to the mobility, and these are what you have to, you know, how to derive, to obtain, just by writing all the approaches that we took, and then we can relate the conductivity to the resistivity as well as to the mobility of the particles. Okay, so we finished with the lecture today. I will stop the recording, then we can stay for 10 to 15 minutes with the questions.